When a bone breaks, we can set it. Pretty straightforward. But what happens when a piece of your skeleton is just gone for good? Well, you can't just stick any old piece of metal in there. The real challenge isn't just about finding something strong, it's about convincing your own body not to attack and destroy the very thing that's supposed to be fixing you.
I mean, really think about that. Your immune system is this incredible bodyguard designed to attack anything that isn't you. A splinter, a virus, you name it. So how on earth does a massive chunk of metal, like a new hip joint, survive that constant surveillance for 20, maybe 30 years? That, right there, is the core puzzle of biocompatibility, and it is a fascinating engineering problem. And it's a problem we've been trying to solve for a long, long time. We're talking attempts with carved stone and ivory way back in ancient times. Fast forward to the 1800s, and surgeons were trying out gold, even lead-coated platinum. The 20th century gave us stainless steel and the first polymers. Each one was a step up, but they all had major flaws. Until one particular material came along and just changed the entire game. And that material was titanium. For decades, it honestly seemed like we'd found the perfect answer. It's incredibly strong, it's surprisingly lightweight, and somehow it had this almost magical ability to fly completely under the radar of our immune system.
So, what's the big secret? Well, it's not magic, it's chemistry. You see, titanium spontaneously forms this incredibly stable, super thin layer of oxide on its surface. And this layer is chemically inert. It basically acts like a perfect stealth cloak, making the metal completely invisible to the body. It doesn't corrode, it doesn't leak weird ions, it just sits there. And the body, because it can't see an enemy, just leaves it alone.
But here's the twist in the story. It turns out you can be too strong. You can be too good at hiding. The very things that made titanium the gold standard ended up creating a whole new set of really subtle problems that took engineers years to even figure out. Okay, so the first problem has this really cool name, stress shielding. Your bones are living tissue, right? They need stress to stay strong. It's just like a muscle. If you put your arm in a cast and don't use it, the muscle wastes away. Well, the same thing happens here. When you put a super stiff titanium implant next to a bone, the implant ends up carrying all the weight. The bone, now shielded from its daily workout, gets lazy, it gets weak, and it can literally start to dissolve away. And this chart just shows you how crazy that mismatch is. Look at that first bar. That's your natural cortical bone. Now look at the titanium alloy next to it. It's over 5 times stiffer. And some other common implant materials, a staggering 10 times stiffer. That is a massive, massive difference in how they handle the simple load of you just walking around.
Now, this is what that actually looks like. This is a computer model of a femur. The warm colors, the reds and greens, that's bone that's being properly stressed, which is good and healthy. But look at the image with the implant. See all that blue? Those are the areas being stress shielded. That's bone that isn't pulling its weight anymore, and over time, it's at serious risk of just fading away.
And that brings us to the second hidden flaw. Remember that stealth cloak I was talking about? Well, it works a little too well. The surface of titanium is so smooth and inactive, scientists call this bioinert, that your bone cells just can't get a grip. They kind of slide right off. But for an implant to really last, you don't want it to just be ignored. You need the bone to actively grow onto it, to grab hold of it, and truly make it part of the body. So the next chapter in this whole quest was about solving these two big problems. How do you make an implant that's strong but not too stiff? And how do you change its surface from a slick wall into more of a welcoming handshake for your bone cells? The answer was to start engineering the surface itself. And this slide really lays out the big shift in thinking. On the left, you've got the old way, a bioinert surface that's just ignored. But on the right, that's the new goal, a bioactive surface. Instead of being smooth and slick, these new surfaces are deliberately designed to be like a welcome mat, inviting those bone cells to come on in, attach, and start building a new home. And scientists came up with some unbelievably clever ways to do this. They're using things like acid etching to create microscopic little pits for cells to anchor into. They developed coatings of hydroxyapatite, which is the actual mineral that your bones are made of, basically tricking the body into thinking the implant is already bone. They even use lasers to create these incredibly complex patterns at the nanoscale. Just brilliant stuff. Now, these surface treatments were a huge leap forward, no question. But the real holy grail, the technology that could solve the stiffness problem and the bonding problem all at the same time, well, that technology is here, and it's 3D printing. So here's why this is such a game changer.
The whole process now starts with you. We can take a CT scan of your specific anatomy and create a perfect digital blueprint. This means we're no longer trying to fit a standard-sized implant into a unique person. We are printing a unique, one-of-a-kind implant specifically for you.
And this is how it builds a fundamentally better implant. A traditional one is just a solid chunk of metal, but a 3D printed implant can have an internal lattice structure, kind of like a scaffold. This lets engineers precisely tune the stiffness to perfectly match your bone, which solves the stress shielding problem. And all those tiny pores, they are the perfect invitation for your own bone to grow right into the implant, creating a truly permanent living bond. And you can literally see the results right here. On the right, that's a traditional solid implant. Notice those bright red spots? Those are high stress concentrations, which isn't good. Now look at the advanced design on the left. The stress is spread out so much more evenly, so much more naturally. It looks almost exactly like it would in a healthy, whole bone. This is engineering that works with the body, not against it. And this graph is the hard data that backs it all up. That blue line down at the bottom, that's our target. That's the stiffness of natural bone. The steep black line way up top, that's standard, solid titanium, way, way too stiff. But now look at the orange and green lines. Those represent the new, advanced designs. See how they are tracking much, much closer to that natural bone line? We are finally closing the stiffness gap.
So, we've gone from carving stone to 3D printing personalized implants that can become one with our bodies. It's amazing. But the story doesn't stop there. The final kind of mind-bending question is this: what if the perfect implant isn't permanent at all? What if we could print a temporary scaffold from a metal like magnesium that supports our bone while it heals and then simply and safely vanishes, leaving only healthy, natural bone behind? That's not just engineering a replacement anymore, that's engineering our way back to ourselves.